But there is some method which proves that it is equal to 1 by 8. How is it possible, sir?
Yes. So this is very good that you're doing so much experimentation. This is wonderful, actually. So here's the problem with that. Minus one. This sum was essentially Ramanujan's own way of saying you can't do arithmetic with divergent series. So obviously, we all know 1 plus 2 plus 3 plus 4, etc. diverges. So it approaches infinity. In the same vein, 1 minus 2 plus 3 minus 4 plus 5 minus 6 ... is equal to diverges again. But in the same way as a sine wave, this just never stops going up and down, never approaches one value. But if you try using arithmetic on this, then it will lead you to an answer of -1/4. And so you could do this. 1 plus 2 plus 3 plus 4 ... equals x. And so then you subtract -2, -4, -6. Oh, wait, no, actually. You subtract -2, -4, -6, and so on. So this is -2x. And eventually, you end up getting... Wait, no, sorry. Doing the exact opposite of what I'm supposed to do. So, get x right over here. Then what we do is we make all these even numbers negative. So originally we have 1 plus 2 plus 3 plus 4 plus 5 plus 6, ... Then we get minus 4, -8, -12, and so on. So this is going to be -4x, which gives us 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus ... is equal to -3x, which, since this is 1/4, sorry, didn't mean to put this negative here. Since this is 1/4, then x turns out to be -1/12. And of course, the method that he has shown is also correct. For anyone who wants to get the gist of it, basically all he was doing was summing over these trios of numbers and realizing that they were all factorizable by 9 and that they gave the same thing inside. And this is just one of the pitfalls of trying to do arithmetic with divergent series. The whole thing comes from, this whole thing is already divergent, and it should be absolutely clear that it is. So, when we're doing arithmetic with it and other divergent series, we're basically doing arithmetic with numbers that don't exist. Hence, we're getting weird results like -1/8, I think that's what he got, is equal to -1/12. So essentially, the lesson that's to be learned, and the lesson that Ramanujan was trying to show by pointing out this is equal to -1/12, is to never do arithmetic with divergent series like this. If they're convergent infinite series, like the example that you might have done in your class, √2, √2, √2, and so on and so forth, if they're convergent series like this, it's perfectly fine to go on and do them. But if they're non-convergent series, if they're divergent series, like this one clearly is, then it's just advisable to never do arithmetic with them regularly. So it's a very big pitfall, but it's an interesting question. And of course, Ramanujan spent a very big chunk of his life working on these peculiar infinite series. So thank you. So that it's the sum of your force of all of the infinitesimal forces over time that you exert on the object. So essentially, all of this definition just corresponds to exerting a force on an object over a distance. So that's how this is related to the actual physical definition.
Next question. Next questions from your side. Yeah.
First of all, good morning, good afternoon, sir. My question to you is, what if there were a number between every pair of real numbers? How would it affect the number line?
Okay, so this is what the whole subject of real analysis is for. So there's what we call the Archimedean principle. Essentially, it states between any two numbers, there can't be another number. So here's how we actually prove that. It relates to the harmonic series. So it's the series where you have 1 and, okay, this is 0 right over here. So you have a half, 1/3, 1/4, 1/5, 1/6, 1/7, and they just keep getting closer and closer together till you can no longer tell the difference between them. Everyone knows what series I'm talking about, right? So, essentially, what we're assuming here is that if we zoom in enough, maybe there's some space between the last number and 0, right? Maybe there's just some little number that we can find right in between. So, then here's what we're going to do. We're going to say that that number that we can find is going to be, let's say, n, right? And so, we want to find some number n such that it's less than 1 over m for all integer m. All m in the integers. Well, not in the integers, but in the natural numbers. So we want n is less than 1 over m for all natural m. So essentially, what we're saying is we want the product mn to be less than 1. But then, here's what I'm going to say. Let's say this is true. And then we find the greatest possible n, right? So let's say n is the maximum value that is still lower than 1 over m. So then, take this. N has to be less than 1 over m plus 1 as well. But then here's what that would imply. M plus 1 times n is less, wait a second. M plus 1 times n is less than 1, but mn is also less than 1. So, wait, crap, I'm forgetting the proof of the Archimedean principle. Okay. Let me try to go about it this way. Let me remember for a second. Okay, I think I got it. So, essentially what we're doing is we're assuming that we have 0, and then we have some last number of the harmonic set. And then after that, there's got to be something in between 0 and that last element, whatever it might be. So then, we're going to let that be n. And so, n is going to be the supremum of the set between 0 and 1 over m. So essentially, it's going to be that it's going to be the maximum of the numbers between 0 and 1 over m. So essentially, it's going to be the last real number that's less than 1 over m. But then here's the problem with that. Because if it's the last number that's less than 1 over m, and 1 over m is greater than 1 over m plus 1, that would necessarily require that 1 over m plus 1 is less than n. Okay then, so let's move to the number that's smallest than 1 over m plus 1. But then the same logic repeats. But this time we use 1 over m plus 2 instead. And we can just keep getting smaller and smaller and smaller. And there's no way that we can find something that's wedged in between the last number of the harmonic series and 0. Now, why did we talk about the harmonic series for so long and 0? Because that seems entirely unrelated to the question. But now, since we were asked what would happen if we inserted a new number in between each number of the real number line? Well, if we look at each number on the real number line, there literally is no space to put anything between them. But hypothetically, if you somehow were able to zoom all the way in, put a new number in between them, that would, I guess, double it. So it would just distort the positions of everything by 0.5. but there literally are no new real numbers to add, since all of them are already covered on the real number line. There are no missing numbers between one real number and the next, which we can prove via the Archimedean principle. And you might say, but the Archimedean principle is only at 0. Well, all you have to do is add some certain number to the harmonic series. If we want to show it's true at n, then we add n to the entire harmonic series. This is n plus 1, this is n plus 1/2, this is n plus 1/3. Then you can see that the same exact logic follows. Doesn't matter where you put it. So, in short, there are no missing numbers on the real number line. But, hypothetically, if you manage to add one anyway, then it would just add a 0.5 times multiplier to the real number line. I hope it answers your question. Thank you.
I have one question that here the y this question is that here the y-axis the slope is undefined, but x-axis slope is 0. But we know that when two perpendicular line is there, the slope product is always -1. How it is?
What?
Means we know that y it's perpendicular, right? So it is 1090 degree. So it's undefined. And x-axis it is 10 0 degree. It's equal to 0.
Okay, so?
So we know that the product of two perpendicular lines is -1.
Okay. So, let's clear this up a little bit. This is what we call division by 0. Because it's not inherently that the product is going to be -1, but rather, if we have two perpendicular lines, one is going to be this. Let's just use mx for simplicity. One is going to be this, and the other one is going to be the negative inverse. But you literally can't take the negative inverse of x. It's going to be -1/0, which I suppose technically does point in the y direction, specifically in the direction of negative infinity, but it legitimately doesn't mean anything. It doesn't mean anything to multiply -1/0 by 0 because, I mean, you can't divide 0 in the first place. You're doing math with indeterminate numbers. So, it's actually, what? Can I remove this? Okay. So, essentially, all that's happening here is we're doing a division by 0, which is just undefined when we have a slope of 0. So, technically, you could say that the slope of the of the y-axis is -1/0, which is negative infinity. So it does reconcile, but it actually doesn't quite mean anything. So the long story short, just don't divide by 0, because when you do, it leads to situations like this. And anyway, there is no such thing as the product of 0 and 1/0. It's not just not equal to -1, it's not equal to anything. So, really, it works for any other slope except 0, because then you're just dividing by 0. It's like the function 1/x. It's defined everywhere except 0. In fact, the exact function is -1/x, since that's just the slope of any line that's perpendicular to anything with a slope of x. So essentially, just don't divide by 0, because when you do, it leads to things like this. Thank you.
Sir, this was.
Okay.
Person A lives in a flat plane and person B lives in a spherical plane. How will they know what kind of plane will exist in?
Okay, so this is actually the main concept of general relativity, the intrinsic curvature that any surface holds, that an observer can measure. And essentially, it utilizes something called parallel transport. So, imagine you're in a flat space, and then you don't know you're in a flat space. But let's say you want to test it out. Then you go in a path from point A to point B to point C, and all the way back to point A. So this is a circular loop. And now what I'm going to do is at every single point, I'm going to draw the tangent vector. So what does that mean? Well, we have the tangent vector over here, the tangent vector over here, the tangent vector over here, tangent vector over here, the tangent vector over here. And essentially, why do we care about this? Well, essentially, we want the tangent vector when we finish to be the exact same as the tangent vector we had when we started. And of course, it is. When we finish, we are about to travel in this direction again. But when we started, we were also traveling in this direction. So boom, the tangent vectors are the same. But now, let's say I live in a spherical coordinate plane. I try to do the same thing. I try to go from A over to B, over to C, and what I perceive is a triangular path. So I try to go in this direction, to this direction, to this direction, and I see what the tangent vectors are. So at first the tangent vector is like this. But then, when we return home, the tangent vector looks like this. These two literally can't be reconciled. They're completely perpendicular to one another, which means there's some amount of non-zero curvature. Or one more thing you can do is, on a flat plane, let's say you have 3 right angles. You can never connect 3 right angles to make a triangle. A triangle must have 180 degrees. So we have one right angle, and then the other 2 points must be less than a right angle. But that's not the case on a sphere. If we draw a sphere, then we can have all 3 points be locally right angles. So we can have this point right over here be a right angle. Then we can have this point right over here be a right angle. And finally, we can have this point right over here be a right angle. So essentially, over here, we can have 3 right angles in a triangle, while here we cannot. So the curvature of a space, you can technically say, depends on the maximum angle sum of a triangle. But of course, that's not the most reliable way to measure intrinsic curvature. So once again, it mostly depends on parallel transport and tangent vectors. But if you want, that's a simpler explanation without vectors of how you can tell you're in a curved space versus a flat space. Thank you for the question.
Good afternoon, Professor. I am Pranjal Nath from class 11th of JEE batch. I have a doubt regarding the concept of factorial. The 0 factorial has troubled me for a very long time. I would like to know the concept behind it and why it is, how it is, and what is the practicality of it, of its existence.
Okay, so 0 factorial is usually just to make power series look good because, and I'll explain this in just a second. So first of all, why do we define 0 factorial as equal to 1? Well, here's the thing with factorials. What we want is that n factorial is equal to n minus 1 factorial times 1. So here's the thing. 1 factorial is obviously equal to 1, right? So then let's plug 1 in as n in this equation. 1 factorial has to be equal to 1 minus 1 factorial times 1. So 1 has to be equal to 0 factorial times 1. So how can 0 factorial be anything but 1? And when it comes to practical application, well, you'll find that it's mostly used in the Taylor series for e to the x, which turns out to be x to the n over n factorial, which means that the constant term is just going to be x to the 0 over 0 factorial, plus x to the 1 over 1 factorial, plus x squared over 2 factorial, and so on and so forth. And of course, x to the 0 is 1, and then 0 factorial also has to be equal to 1. And that gives us the correct behavior for e to the x. So essentially, the practical application of it lies entirely in the Taylor series for e to the x. And its definition as 1 simply lies in the definition of the factorial as being the previous number times the current number. The previous factorial times the current number. So I hope that answers your question. Thank you.
Clear? So my question is that if there are 100 dots in a plane, all equally spaced, how many number of squares can be formed by joining any 4 of these?
How many? How many?
100 dots.
Okay. How many squares can be formed?
Yeah.
Okay. So that's a very nice question, and here's how I would solve it. So, of course, at first you would think it just 100 choose 4, because the square has 4 rectangle. Wait, it's only squares, not rectangles. Okay, so it's 100 dots equally spaced out on the coordinate plane. So how many squares can we form? Oh, that's an interesting question. All right, so here's what I'm going to do to solve this. So we're going to, of course, set this to be 0, 0. And, of course, every new one to be 1, 2, 3, 4, and so on and so forth. So we're going to go all the way to 9, 0. So how would we actually figure out how many squares there are? Well, here's what I would do. I would simply do kind of a procedural approach, right? Because, okay, so here's what I would do. So, no, that's going to create double counts. So what can we do? Well, I suppose the only thing we can do is just go bit by bit. Go from squares with a length of 10 to squares with a length of, no, not with a length of 10. Squares with a length of 9 to squares with a length of 8 to squares with a length of 7. Squares with a length of 6 to 5 to 4 to 3 to 2 to 1. That seems to be the best approach I can think of here. And of course, 9, there's just 1 square that can act this way. 8, there should just be 4 squares that act this way. 7, there were just 9 squares that act this way. 6, there were 16 that act this way. 5, there were 25 that act this way. 4, there were 36 that act this way. 3, there are 49 that act this way. 2, there were 64. And 1, it should be 81. And so, all we have to do now is just sum all of these squares, which I forget what the equation is, so I'm just going to have to do it manually. Just 145 plus 85 plus 41 plus 9 plus 4 plus 1 is 14. So you get 55 plus 85 plus 145, which means that it should be equal to 285. So do you have any question on how the logic of that works? Well, actually, I should clarify it myself. So here's how the logic of that actually works. So first of all, it should be obvious that there's only 1 square with a length of with a side length of 9. So I'm going to draw the 100 dots very quickly. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 20, 21, 32. That's 50, 60, 70, 80, 90, and 100, equally spaced. So now it should be pretty obvious how many squares there are with a side length of 9, of course. Actually, I'm not going to draw them with dotted lines. Way too bad to undo. So it should be pretty obvious there's only 1 square with a side length of 9. But now, when it comes to squares with a side length of 8, we have 4 choices. Why? Because we can choose to put it here. We can choose to put it here. We can choose to put it here, or we can choose to put it here. So essentially what I'm saying there is we have 4 choices for what the top left corner can be. So then, for the 7-sided square, we have 9 choices for what the top corner can be. For the 6-length square, we have 16 choices on what the top left corner can be, and so on and so forth. So essentially, it's just a sum of squares problem that leads to the answer 285 possible squares. I hope that's correct, and I hope it answers your question.